Let's use what we just learned with linear systems of inequalities and apply it to this real-world situation. It says Malcolm earns $20 per hour mowing lawns and $10 per hour walking dogs. His goal is to earn at least $200 each week, but he can work a maximum of 20 hours per week. Malcolm must spend at least 5 hours per week walking his neighbor's dogs. For how many hours should Malcolm work at each job in order to meet his goal? What we'll do is we'll create a system of linear inequalities to determine the best amount of time spent at each type of job. We've read through it, so the next thing we should do is determine what our variables represent. Well, we want to know how many hours he works at each job, so our variables should represent each type of job. I'll let X equal hours mowing the lawn. And then let's let Y equal the number of hours walking dogs. Now let's take a look at some kind of key information on our graph. You'll notice the graph doesn't include all 4 quadrants. This is because we can't have negative hours of dog walking or negative hours of lawn mowing. So we're only going to use values for X and Y that are greater than or equal to 0. Because of that, we can state part of our system based on that information. We know that X would have to be greater than or equal to 0 to represent the fact that he has to have positive hours mowing the lawn. Same with Y. But we also know a new thing about Y. Malcolm must spend at least 5 hours per week walking dogs. So not only is Y greater than or equal to 0, but Y also has to be greater than or equal to 5. So that affects the shape of our graph. It says together he can only work a maximum of 20 hours. So he doesn't have to work 20 hours, but that's the most amount he can work. What that means is the number of mowing hours together with the number of dog walking hours must be less than or equal to 20. Let's see, what else do we have? Oh, at the very beginning, looking at the amount he gets paid. So this is kind of the ultimate goal to decide here. How many hours should he mow and walk in order to earn at least $200? He gets paid 20 hours for mowing. That means each hour we would multiply it by 20. Walking dogs is a little bit less, so for each hour he walks dogs, he gets $10. And now again, he wants at least $200 per week. We want this amount to be greater than or equal to 200. Well, I think that's all we have for our system. So let's take a look one more time. Read through the word problem and see if there are any other inequalities that we need. I think we got it all covered. So now the fun part, the graphing. You'll notice on the right, I drew the line on the bottom and on the top. So we need to figure out how to best use our space. I'm going to really stretch this out, and I'm going to put 20 all the way at the bottom of my graph. Pause the video and see if you can divide your graph up accordingly. So each kind of bar would be one total unit. I didn't list all of them, I just kind of spread it out as best I could, and those are all the hours mowing lawns. Then press play, and then we'll do the same thing with the dog walking. And now your graph should look something like this. So I divided it up evenly. It won't always have to be even. Like you won't always have to have 20 on the far right and 20 at the far top. It just kind of depends on our situation. All right, once your graph is set, let's take a look at graphing our systems of inequalities. Taking a look at the first one, X is greater than or equal to 0. What that means is we're going to have a vertical line, and really anything on this part of the graph is fair game. And then for Y, greater than or equal to 0, well, we know that this is true, and it would be everything above, but then this one kind of beats the first one, not really beats it, but kind of overrides that rule. We actually want Y to be greater than or equal to 5. So instead of shading down below, I'm going to shade right where 5 is. So I'll draw a line straight across for 5, because that's more of a restriction on our output than the 0 will be. So far our overlap is still a pretty big rectangle. Now let's take a look at x plus y is less than or equal to 20. I'm going to subtract x and write it as an inequality y is less than or equal to negative x plus 20. What that means is our y-intercept is 20, like so, and the graph is going to go all the way down to 20 on the bottom. That would be the x-intercept. And this is going to be a solid line. They're all solid, aren't they? I'll connect all the way down as best I can, like so. That means anything less than that, so we're now cutting our space pretty significantly. I think now the only thing that overlaps is a right triangle. So the ultimate deciding factor is going to be that last inequality. The 20x plus 10y is greater than or equal to 200. I'm going to subtract 20x to the other side and write that down below. 10y is greater than or equal to negative 20x plus 200. To get y by itself, we'll divide both sides by 10, and that's y is greater than or equal to negative 2x plus 20. On the graph, that means this is going to have an intersecting y-intercept at the top, but then all the way at the bottom, if we want x to equal, or if we want y to equal 0, then x would actually equal 10. So now this shape is going to connect, or this line is going to connect like so, but this is greater than or equal to. And so now, oh boy, what a mess right here, you guys. There's a lot going on. I think we've graphed all of our inequalities. What we need to decide is where is that major overlap? Where does everything intersect together? And then that'll help us determine our final answer. I notice the boundary at the bottom is that 5 for the y values. The blue is kind of everything in that section, so we can pick anything there. The red and the purple and the green seem to make this oblique looking triangle. So I'm just going to try to darken this in a little bit. This is where the overlap is. So in this shaded solution, it's just fun to color. In this shaded solution should be the amount of time that Malcolm can spend at each of his jobs. So it says for how many hours. So we actually have more than one example. Our final solution, there are multiple options or multiple solutions. We'll just give a couple of options. So what we need to do now is actually go into the graph and determine an x and a y value. Let's see, if I go over to 8 on the x-axis and up to 8, I notice that's in that solution set. So we could do 8 and 8, 8 hours of each job. That would work. Can you come up with another one? We could even do half hours if we needed to. We could do, looks like we could do 12 and 5. That appears to be within that limit. So he could mow lawns for 12 hours and then walk dogs for that minimum of 5. Or that'd be 6, wouldn't it? Well, we could do 5 too. 5 would work, but I think I put 6 in where my dot is. So there are lots of options. We're just trying to figure out any values in that darkened in set where that overlap is. And there's a little bit of application of how to make this apply to some possible real-world situations.